Okay, so let's talk about chapter 7 again for today. So, well, keep in mind that this is going to be 20% of your final exam. Uh, the big portion gonna be on the application of differentiation and integration technique. So make sure you study on those two chapters. So last time we talked about regions between curve, and we know that if we have two curve and we can find the region between them. For example 178 like that. Well, 1 second, it's coming. So 178. So I have a graph of sine and cosine. I can find the area between them, the one that I highlight in light blue. So the idea of finding the area is to figure out which curve is on the top, which curve is on the bottom, and then you just integrate from the bottom to the top one. Well, then you can choose to integrate dx or integrate dy. It depends on you. Well, sometimes it's going to be easier to integrate with respect to x. Sometimes it's easier when integrate with respect to y. So easier means you don't have to, cut the region into two pieces. For example, if I have the region like example 180. So this is, well, the internet is just so slow. So the region is easy to integrate with respect to y because you don't have to split your region into two pieces. But if you integrate with respect to x, you have to integrate by splitting the region into, from -6 to 0 and 0 to 2, like in this example. All right, that is what we did last time. So now it's 3:05. I think it's time to start a new one. I think we gain more students now. So we have 19 students. All right, let's move to the next topic. I think you ready? All right, so section 7.2, volume by slicing. So the idea of this section is we are going to find the volume of the solid. So the solid that we are going to be interested in is going to be the solid that when you cut the solid perpendicular to x or y axis, and then you're gonna get the cross section with the same shape all the time. For example, if you look at the solid that I circle here, you can see that the solid that I have the yellow thing here, if you cut the solid perpendicular to the x-axis, so you can see that the cross section is going to be the same shape all the time, no matter what x value you cut. So you're gonna get the same shape, which is the uh, open down parabola. Does it make sense? And then that means you can find the area here. Well, in terms of x, because no matter what value of x you cut, so you still get the same shape, and then that means you can find the area of that cross section. Well, you can imagine that when you have the volume or when you have the solid here from A to B, you just chop into n pieces, and for each piece you're gonna have uh, the width delta x here. This is going to be your width for each each piece, and then you can multiply delta x with the cross sectional area to get the volume, right? And then after that, if you sum it all, and then you just take the limit when n go to infinity. So this is going to be integral. So the volume is going to be integrate from a to b of ax dx by you just find the cross sectional area, and then you just write it in terms of ax, and then you just integrate from a to b. Well, if you have a hard time to imagine the picture. Think of when you have a loaf of bread. When you have a loaf of bread, if I ask you, hey, can you find the volume of the loaf of the bread? So the easiest way is you just cut the loaf of bread into n pieces, right? And then you just compute the volume for each piece. And then for each piece, you're gonna just find the width, and then you multiply with the cross-sectional area. So you get the volume for each one. And then after that, you sum it all. So you sum n pieces. So you're gonna get the volume of the loaf of bread. So the same thing here. All right, when it's come to the real problem here, we're gonna call this thing general slicing method. So you're gonna be given the solid, and then you're gonna need to find the cross-sectional area AX. Well, I call function A to be my cross-sectional area. And then once you get your AX, you put it in the integrand. And then after that, you integrate from A to B, where A and B are your lower bound and upper bound of your X interval. Does it make sense? Once you set up, you're done. The rest of the work is going to be just basic integration. So the proof is here if you want to read, but the idea is I just explained to you a few minutes ago. So the idea is you just chop your volume into n pieces, and then you just compute the volume for each piece, and then you just sum it all. And then when you do the continuous sum, it is going to be an integration. All right, it's going to be better after you look through examples. So before we look through the example, so let's sum it up one more time. So if they ask you to find the volume by using the slicing method, so first of all, you need to know the base uh, region R. You sketch it, and then after that, you need to find the formula of the cross section, and then you find the limits of integration, and then you just put everything together so you get a volume. So let me show you a quick example here. Well, after you see example, I hope you can connect everything and see how it works. All right, so example here. So let's suppose that I wanna find the volume of the parabolic cube. So I let R to be the region in the first quadrant bounded by the coordinate axis, and the curve y equal to 1 minus x squared. Its solid has a base R, and cross sections through the solid perpendicular to the base and parallel to the y-axis are squares. Find the volume of the solid. So you can imagine that when you do the problem, so you're gonna start by, hey, we need to figure out R first. So the question say, let R be the region of on the first quadrant bounded by x-axis, y-axis, and parabola. So in the real problem, you may need to draw the graph. This is y-axis, this is x-axis, and then you draw the parabola here. This is y equal to 1 minus x squared. This is your parabola, right? And then now you need to find the region R. So the region R here is going to be on the first quadrant, bounded by axis and this curve. So it's going to be here. This is going to be your region R, right? Bounded by x-axis, y-axis, and parabola. So this is your region R. Well, the question said that, well, you're gonna form a solid whose base is R. So your R gonna be your base, and then you do the solid such that the cross section perpendicular to the base and parallel to the y-axis. So that means you cut. Well, look at the picture I just drew. So I just cut the solid parallel to y-axis here. You can see that the purple line here. So every time I cut, I am going to have this square. So if you look at the 3D picture, it's going to be like that in 3 dimensions. So you can see that I have the parabola here on the base. And every time I cut parallel to the y-axis, I am going to have the square. And then after that, if I do that for every x value, so I'm going to get the solid. Does it make sense? Well, on the exam, you are not required to draw a picture. What we need from you is we need you to set up the equation and draw the region for the base. So if you draw the region of R, and then you can imagine that your AX is going to be 1 minus x square, then you done, you integrate from 0 to 1. Well, let's see how do I know that AX is equal to this function. So you can see that your AX, it's going to be the area of the square here that I just shade in red. So the area of the square here gonna be the side square, right? So I need to know the length of the side, and for each x value here, that I'm gonna have the length of 1 minus x squared. So 1 minus x squared is the length of, side of the square, right? Because your parabola just start from y equal to 0 to y equal to 1 minus x squared. So that means the length of the side of the square, this is going to be 1 minus x squared minus 0. So that 1 minus x squared gonna be just the height here, and then you square it, so you get the area. And then you put ax in the integrand, so you integrate from 0 to 1, which is going to be the x value from 0 to 1 here, then you're done. Right, so you integrate from 0 to 1, 1 minus x squared square dx. Fine. Does it make sense? Well, this topic, this is the hardest one for chapter 7 in my opinion, because usually students did pretty bad on this thing, like based on my experience, because it's require your imagination a little bit, that hey, you have a base here, and then you have this is a solid, and then you just need to cut it, you get a cross-sectional thing. So we have 3 examples today, and for sure this is going to be one big question on the exam. So if you do not want to skip this topic, so you have to absorb the technique from the following 3 examples. All right, so we're gonna start by looking at example 181. So let's do this one together. So I have a solid of, let's read the question together first. So I have a solid that the base is a unit circle, x squared plus y squared equal to 1. So the base of the solid, this is the solid, and the base of the solid here is just a circle, x squared plus y squared equal to 1. The cross section through the solid perpendicular to the base, so perpendicular to the base and parallel to the y-axis are equilateral triangle. So that means every time when you have a solid here, and you know that the base is your circle, every time when you cut parallel to the y-axis, every time you cut parallel to the y-axis, look at the purple line I just drew on the graph, on the picture. So every time you cut parallel to the y-axis, you get equilateral triangle. Does it make sense? And if you do that for every x value, this is going to form a solid for you. Sounds good? So what you need here is you need v equal to integrate ax dx from a to b. So what is going to be your a and what is going to be your b? So to figure out your a and your b, so your a gonna be your first point that you cut the purple line, which is x equal to -1. and the last x value that you cut is going to be 1, right? Because in order to form the solid, you need x value, like you need to just cut perpendicular to the base and parallel to the y-axis from x equal to -1 to x equal to 1, right? So x is going to be -1 to 1. Sounds good? And then now I need ax. So ax is going to be a little bit tough. Ax, this is going to be the area of the cross section. So what is going to be the area of the cross section? So how do you find the area of the cross section? So the base is the circle, right? This is your base. This is your base. This is just a circle. You say that every time when you cut, you're gonna cut parallel to the y-axis. You cut here, and every time you get the triangle. So I'm not going to draw 3 dimension here. It's just 2 dimension. This is going to be your side of your triangle. Does it make sense? This is going to be your side of the triangle, equivalent to the black one that I draw here. It's going to be your side of the triangle. So actually, the area of the cross section gonna be the area of the equilateral triangle. So that is going to be square root 3 over 4 side square. How do I know this formula here? Because the area of the equilateral triangle, this is going to be a equal to square root 3 over 4 times s square, where s is the length of one side of the triangle. So if I know that the base of the triangle have the length s, so the area is going to be a equal to square root 3 over 4 s square. So this formula is instant. You can use it. Here I am going to find my side. So my side is going to be square root 3 over 4, formula for the area going to be square root 3 over 4 times side square. So my side, how do I know the length here? So what is going to be my length here? So the top line here that I highlight in light blue here, this is y equal to square root 1 minus x squared, right? And the bottom curve here that I highlight in yellow, in orange, this is y equal to negative square root 1 minus x squared. So that means if I want to find the side here, so the top curve gonna be square root 1 minus x squared. The bottom curve gonna be negative 1 minus x squared. So the length here gonna be square root 1 minus x squared minus square root 1 minus x squared. Everything squared. All right, here, the one that I highlight in orange, this is from the bottom curve. The one I highlight in light blue, this is from the top curve. Sounds good? And then the rest of the work, you just need to simplify it. So you simplify this thing. This is going to be square root 3 over 4, 2 times square root 1 minus x squared square. And that is just all right, and then I plug in square root 3 times 1 minus x squared here. So I get square root 3, integrate from -1 to 1, 1 minus x squared dx. And then you can integrate this thing, so I get square root 3 x minus x cubed over 3. X from negative 1 to negative 1 to 1. Well, you can do it at home. So this is going to be 4 square root 3 over 3. This is your final answer. Well, I already did it. So just plug in the value and replace. All right, so this is going to be the first example on volume by slicing. Well, I read this question star, 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 star. So if I say that, for sure, you're gonna have a similar one on the exam. So study on the type of this question, so it is very likely that you're gonna see the same format of this question on the exam. So make sure when you do the when you compute the volume of the solid by using the slicing method, so you need to find the base first, and once you find the area of the cross-sectional, then you put it in the integrand, and then you just set it up to be your volume. That's good. Sounds good. All right. I feel like you need more example for sure. That's fine. So we're gonna do 2 more on this topic. So hope you feel better on the second and third example. All right. Example 182. Let's do this thing together. Again, 5 star. So it's gonna be the same format like that you're gonna see. Well, even on the homework, you're gonna see the same format here too. So let's look at example 182. So I have, well, this question I did not give you a solid, well, but you still can do it. So let R be the region bounded by the line y equal to 1 minus x, y equal to 2x plus 5, x equal to 3, and the y-axis. So first of all, you need to draw the graph of R, and then the graph of the region R. Sorry. Next, a solid has a base R and cross section through the solid perpendicular to the base and parallel to the y-axis R square. All right. We have to draw the base R first, and then we know that if we cut parallel to the y-axis, you get square. Now, find the volume of the solid. Okay, good. So we're gonna draw R first. So just go slow. So we need to draw the R. So we're gonna have y-axis, and we're gonna have x-axis here. The first one gonna be y equal to 1 minus x. All right, so it's gonna pass x equal to 1 here, x equal to 2 here. All right, y equal to 1 minus x. The next one is y equal to 2x plus 5. Okay, I'm gonna draw this thing 2 and 1. So, all right, good. Is that right? 1 second. It's gonna be 1 and 1. So I don't know why I say 2. Stupid me. It's gonna be 1 and 1. So x equal to 1, y equal to 0, y equal to 0, x equal to 1. Sorry, 1, 1. All right, y equal to 1 minus x. Sorry. Next is y equal to 2x plus 5. Y equal to 2x plus 5. So that means I cut the y-axis at 5. So it's going to be here at 5. All right. Well, and it's cut x-axis at somewhere. So I don't know. So just keep it going. Y to x plus 5. Now x equal to 3, which is this line, right? X equal to 3. All right, and the y-axis. Okay, that means x has go down to that. So that means I have the region I want now. So the region I want is the one that bounded by the curve y equal to 1 minus x, the curve y equal to 2x plus 5, the line x equal to 3, and y-axis. So it's going to be this one. Would you agree? Everything here, well, the scale is not proper, but this is everything I have here. So the region that I highlight in orange, this is the one that bounded by the line y equal to 1 minus x, y equal to 2x plus 5, x equal to 3, and also the y-axis. Well, if need, you can find the intersection, but I'm going to just go ahead to find the area of the cross section. So the question say that, well, you need to find the volume of a solid and the cross sections parallel to the y-axis. So that means every time when you cut here, parallel to the y-axis, this is how you cut it. So you're gonna have the square. and if you sum up all that areas, that square, so you're going to get a solid, right? So that's mean you need to find the area of the cross section first. So area AX is going to be just, well, you need a square, so the formula for the square going to be the side square, right? And how do you figure out the side? So the side going to be just, well, the top line minus the bottom line, the top line minus the bottom line. Luckily that the shape that you have here, you use the same top line, which is going to be y equal to 2x plus 5. You use the same bottom line, which is y equal to 1 minus x. So this is going to be 2x plus 5. This is from the top curve minus 1 minus x. This is from the bottom curve. And then you square it because this is the green line, right? This is the purple line. So if you do the green minus purple, so you get the length of the side depends on x, right? And then after that you square it, so you get the area of the cross section. So the cross section area here gonna be your integrand for your integration, and then you integrate from a to b. All right, so let's put that thing inside. So I'm gonna simplify first. So we get 3x plus 4 square. All right, so I'm going to integrate 3x plus 4 square dx, and then I integrate from a to b. So what is going to be my a and my b? So for sure I start from, so I have to think what is going to be the first x value that I cut here. So the first x value that I cut is 0. The last x value that I draw the vertical line is x equal to 3. So it's going to be 0 to 3. All right, and if I integrate that thing, so I'm going to get the answer I want. So I'm going to get 3x. Well, I think I'm going to expand that. So 9x squared plus 24x plus 16 dx. Well, and that means I get 9x cubed over 3 plus 24x squared over 2 plus 16x. And then integrate from 0 to 3, 237. I already did it at home, so you can do it slowly by your own. Well, on the exam, maybe we're gonna just ask you to stop at this point. You know, well, if you read the question and it says do not evaluate, just need to set up, you can stop the answer here. So you do not need to simplify more and compute more. If I ask you to just say, hey, stop, just set up, you're done. Just this one. Does it make sense? All right, feel better after 2 examples? I hope. All right, let's do one more. All right, example 183. Let R be the region bounded by the curve y equal to square root x, absolute x, and y equal to 2 minus x squared. A solid base R has a base R. The cross section parallel to the y-axis is a semicircular disc, right? An integral you would use to find the volume of the solid. Do not evaluate integrals. Here, you see what I asked? Can you write an integral you would use to find the volume of the solid? Do not evaluate the integral. So that means you just need to set up the integrals, and then that's all. So first of all, we are going to find the region R first. So let's draw the graph. So y equal to square root x. All right, that is easy. All right, the next one is 2 minus x squared. Right, it just open down parabola, but just shift up 2 units. So the area that you want, it's going to be the one that bounded by these two curves. All right, this is good. Well, we got the region R easily, right? Now, what we want is we want to find the volume of the solid, and we know that the solid has a cross section that cut parallel to the y-axis, and we get semicircular disc, which is going to be, you know, something like that, semicircular disc. Right? What is the area of the semicircular disc? So the area of the circle is pi r square. Right? So the area of the semicircular disc is going to be 1/2 times pi r square, because if you have the radius r, so your area going to be just pi r square half, because this is half circle. All right, it means every time you cut perpendicular to the x-axis or parallel to the y-axis, so you get the semicircular. Like every time you cut, you get semicircular. Every time you cut, you get semicircular, and it's gonna form you the solid. And then we want to find the volume of that solid. So what should we do then? All right, so we're gonna find the area AX. So the area AX, this is going to be, you need to have the, what we say, the green line on the top, right? And the purple line on the bottom. This is going to be your diameter here. Does it make sense? Your diameter here, the red one, going to be the top line minus the bottom line. So you have the top line, which is going to be 2 minus x squared. And then you minus the bottom line, which is your absolute x. This length gonna be the length of your diameter. And then you divide it by 2 to get the radius, right? This is going to be your diameter. Let's say again, this is your diameter. And then if you divide it by 2, you get the radius. And then after that, you square the radius. And then you multiply pi over 2. So this is going to be the area. Color. So the area gonna be just pi over 2 times that term, right? And then when you want to find the volume, it's going to be integrate ax dx from a to b. So what is going to be your a? What is going to be your b? So your a gonna be this point. Your b gonna be this point, right? Well, your a gonna be the x value correspond to this point. Your b gonna be the x value from this point. So just tell me in the chat, what is your a and b? Well, you need, at this point, you need to know how to find the intersection. Well, how do you find the intersection? So find it and give me in the chat what is your a and b. And then once you find your a and b, you can plug in that. So I'm gonna keep everything here. Oops. It's a little bit hard. All right, dx. All right, so what is going to be your value of a and b? Plus and minus root 2, negative 1 and 1. All right, 2 numbers. All right, do you know how to find the intersection, everyone? So you need to solve. Well, you need to solve y equal to absolute x and y equal to 2 minus x squared. You need to know where it cuts. So if you can eyeball it, you can see that it's cut at negative 1 and 1, right? Because if you plug in number 1 there, so you're gonna say that, hey, the graph passed the point 1, 1, and the graph passed the point negative 1, 1. This is how you eyeball it. But if you do actually want to solve, so you can do absolute x equal to 2 minus x squared. And then you can think when x is positive, that means you have x equal to 2 minus x squared. And then you get x squared plus x minus 2 equal to 0. And that means you have x plus 2 x minus 1 equal to 0, and that means x equal to -2 or 1. However, because you force that x is positive, so x is 1 is your answer. Here, that means x equal to 1, right? But when x is negative, so you have negative x equal to 2 minus x squared. Because when x is negative, your absolute value going to be negative x. And then after that, you get x squared minus x, this time plus 2 equal to 0. Well, you solve, you factor, so you get x plus 1 and x minus 2 equal to 0. So here x equal to -1 and 2. But because you force that x is not less than 0, so that means x equal to -1. So the intersection gonna be when x equal to 1 and -1, which is good. So we're gonna integrate from -1 to 1. And this is my answer. I can stop here because the question said do not evaluate the integrals. I just need to set up. Do you think you can do this one on the exam, like 5 point? I hope you can, because, well, technically this is not hard, but it just requires a little bit of imagination from you. All right, sounds good. I think we ran out of example for this topic. So we're going to move to the next one, which is the volume of the solid by using the shell method. So any questions in the chat, please? Well, I have a question from Sirapop. He asks, how do we integrate absolute x, right? So if you actually want to integrate absolute x, what should you do? Well, copy this to the next page. So what if you want to integrate this thing? Well, if I ask you, hey, let's integrate it. So what should we do? So we're gonna integrate -1 to 0, right? Pi over 2 minus x squared minus -x and then square over 2 and then dx and then plus integrate from 0 to 1 pi over 2 2 minus x squared minus x squared over 2 dx. So if you want to actually integrate square root x, you can see that your square root x is going to be plus x or minus x, depend on the value of x. So when x is positive, so your absolute x is going to be positive. Oops, no square, sorry. No square here. Squares outside. Okay. And then when x is negative, so your x is going to be negative, absolute x is going to be negative x. This is how you integrate it if you want to compute it to the end. All right. Well, one question at a time. So next from Mr. Pepper. So can you explain why the radius is that value again? So the radius here, well, you can imagine that when you, well, I'm going to use it here. You can imagine that when you have the base here. So the line that I just do the red line here, this is going to be your base, right? Your base. And every time you're going to get the semicircular. Like every x value that you cut, you're gonna get semicircular, right? So that's mean the length here gonna be your diameter. The length here gonna be your diameter, and if your diameter is that length, the radius is going to be the half of diameter. So that's mean, well, 1 second, 2 minus x squared minus absolute x. This is going to be my diameter, and I divided by 2 to get radius. Good. And then after that, I square it and then multiply by pi over 2, so I get the area. Well, but I hope this answered the previous question. All right, Napat, try, is your AX wrong 2 minus x squared. Oh, yes. Yes. Whoa. 1 second. It must be 2. Whoa. Thank you. Thank you for correcting that to me. So it must be 2 minus x squared. All right. I did it too fast, huh? So square must be inside. Inside. Thank you. All right. That is just, I copied it wrong. Nothing wrong about it, just my mistake because I copy it from the question wrong. The function must be 2 minus x squared. Good job, Napat. Napat. Just Napat. All right, Sirapop 7. Can we the positive side and times by 2? Yes. I mean, if you want to compute this thing, so you can compute on the positive side and then you multiply by 2. You can. Yes, you can. Why not? Because the solid is symmetric, so you can. All right, anything else? Well, I'm sorry from that my mistake. I think that's why previous asked the question too. So I copied it wrong. Yeah, but I fixed it. It's just 2 minus x squared. All right, good. All right, this is going to be similar to the homework questions. So I'm gonna show you homework then before I move forward. Well, let's stop share that one. I'm gonna show you homework number 6, which is already on Blackboard, to give you a guideline on that. So let me find my assignment number 6 so we can look at it. Where is it? Okay. So if you look at my assignment number 6, well, for this class, this is going to be due November 28th, just 2 days before the final exam. For question 1, so find the area of the region bounded by these two curves. Well, I force you to integrate with respect to x and integrate with respect to y. So you have to do 2 ways. So draw the picture first and then find the area with respect to x. And that means you use dx. And another one is just integrate with respect to y. You use dy. All right. So be sure you solve a key. So that means your answer must be the same no matter you integrate with respect to x or y. And then next, question 2. Well, this is the one that we learned today. So find the volume of the solid whose base is the region bounded by the curve y equal to x squared and y equal to 2 minus x squared. So that means you have to draw the graph y equal to x squared and you have to draw the graph y equal to 2 minus x squared. And then you're gonna get the base, right? Because this is the base. And then after that, we ask you to find the solid, the volume of the solid, and we know that the cross section to the solid perpendicular to the x-axis are square. So that means when you, well, this question means that after you find R, whatever it is, your area R, so you cut perpendicular to the x-axis. What does it mean, cut perpendicular to the axis? Here, right? Cut perpendicular to the axis, right? You just, the x-axis is here, but the question says cut perpendicular to the x-axis. That means every time you cut, well, but on my example, I say parallel to the y-axis, the same thing, perpendicular to axis. And every time you cut perpendicular to axis, you get square. You get square. Well, as I told you, you don't have to draw the 3-dimension solid because it's going to be messy because this is just a paper. You cannot draw the 3-dimensional solid, but well, you can use your imagination. It's going to be the solid, and then when you cut, you get, every time you cut, you get square. So well, once you just figure out your ax and then you integrate from a to b, ax dx, boom, you're done. Sounds good? Well, now you can do homework number 1 and homework number 2 for sure. Let me delete this thing. Clear. All right, and number 3 is just ask link for next class. Well, we're gonna just learn a little bit more for today, to look at this method. All right, so I'm gonna stop share this thing. So any question in the meantime in the chat, please? So I'm gonna go back to my iPad so we can learn more. Oh, 1 second. I, I think what I think I want to share one more thing. So some of you already know this thing that we have a tutoring section starting from today. So the tutoring section gonna be 4 p.m. to 6 p.m., which is overlap to our class. Well, I'm gonna share the screen in a minute. That I need to 1 second. Just give you a minute break here. So announcement. Here, this is going to be the review section. Here. From 4 p.m. to 6 p.m. on November 16, 18, 23, 23rd, 24th, 25th. So 5 days here, starting from today. Actually, it's overlap to our class, but I already asked TA to record the tutoring section for you. So if you choose to stay in my class, fine, you can ask me for the record of the tutoring section after. Or if you want to quit from my class, go to the tutoring section, that's fine. You can watch my clip after as well. So it depends on you. Pick the one you want. This is the meeting ID and the passcode for the tutoring section. I mean, the tutoring section is going to be the same as midterm. So I don't know about the format. Maybe the TA gonna show up the O exam and then you just work with them. I guess that is the format they do. But you know, you can ask them anything too. Well, but I'm gonna just keep going and I'm gonna stop the class at 4:15 or 4:20. Works. That's my plan. But if you wanna leave the class for the tutoring section, that's fine, totally fine, because I record it anyway. The recording of the tutoring section gonna be, I will give you a link so you can go to that video directly. But for my lecture, I'm gonna post on my channel, YouTube. Sounds good. All right. Next, well, we're gonna just go back to the next topic. All right, so the next topic is volume of the solid of revolution, or sometimes this is called volume of the solid by rotation. For 20 minutes more, just stay with me. I think about 20 minutes to 25 minutes more, and then we are done for today. So let's look at the volume of the solid of revolution. So the idea of this section is not that hard. So it is going to be the same thing with the previous section. The difference is going to be the one that when you cut, if you cut the solid, you always get the circle. Well, this thing is called this method. So let's look at the example together first. Well, I don't want to go too fast. So let's look at the picture here together. So we now consider a specific type of the solid. This is called a solid of revolution. So if you let's think together. If you let fx to be square root x, which is this curve, the green one, and then the green one, and then I say that, well, I have a region R. I bound the region by using the function fx, x-axis, x equal to 0 and x equal to 1. So this is, I bound that. So I get this area in green. I rotate this thing about the x-axis. Sure. When I say rotate, it means I just rotate this thing. I use x-axis to be my axis of revolution. And you can imagine that I rotate, choop, 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 choop. So I get like a bowl here. Does it make sense? I will get the three-dimensional bowl. So this is called the solid of revolution. Does it make sense? For example, if you have just a line here, I mean the region R here. If you rotate this thing around the x-axis, so what you get is you're gonna get a cone, right? Because if you just use the region R here as your starter and then you just rotate about the x-axis, so at the end you're gonna get a cone. Well, the same thing with this, you have the piece like that, square root x bounded by square root x, and then you rotate about the x-axis. You just keep rotating, and then well, once it get the full rotation, so you're gonna get a solid here. So this type of solid is easy to find the volume, because if you cut the volume, if you cut the solid with respect to x, so you're gonna get the cross-sectional area here as a circle shape. So that means you can use the previous section to find the volume here. So let's look at it. So that means, hey, my cross-sectional area AX, this is going to be pi r squared, because I always get circle, right? I always get circle. No matter where I cut, I am going to get circle. So that means my AX here, my AX here gonna be, oh, let me mute that. Okay, my AX here gonna be pi r squared, right? And your R gonna be just fx. Why is that? Go back to the picture. So your R here gonna be, this is your R, right? Your R. Trying to look at the one I drew it in purple line here. So this is going to be your R. And for sure, your R is going to be your function fx minus 0, right? Because you just rotate about the x-axis. So it's going to be just function f minus 0. So that means you are going to be just function f. And then for the previous question, so I rotate the square root x thing. So my r is going to be just square root x. And then I integrate from 0 to 1. So I get pi over 2. This is going to be the solid, the volume of the solid of revolution. And this is in general called the disk method. So the disk method about the x-axis, so this is the formula. V equal to integrate from a to b pi fx squared dx. If you understand the idea behind it, you don't have to memorize the formula, because you always know that your cross-sectional area, you can compute it by compute the area of the circle, right? Easy. All right, so we're gonna, before we start doing some examples, so keep in mind that you can do this for the y-axis as well. So for the y-axis, you're gonna integrate from c to d pi fy squared dy. So it's gonna be just, you know, when you have that, let's say that region R, right? And then now you rotate about the y-axis. So you're gonna get a cone. But you can see that every time you're gonna cut, and then you get the circle as well. If you cut here, you get circle all the time. Well, when you figure out your fy, when you figure out your radius, you're gonna get something in terms of y, right? Because you just look at different axes now. So to sum up the step of the disk method, first you sketch the base. Second, trying to think what is your axis of rotation. And then after that, you're trying to find the radius and find the limit of integration and set it up. Good. All right, so we are going to look at, well, let's see. How many examples do we have here? Two. So we're going to look at 2 examples for today. I think it's going to be the perfect timing for today. So example 184, let R be the region bounded by the curve y equal to x plus 1 square. X-axis, the line x equal to 0 and x equal to 2. Find the volume of the solid of revolution obtained by rotating R about the x-axis. So first of all, you need to draw the graph, the region R. All right, so we are going to draw, okay. Some of you are gonna say, Ajahn, how do I graph y equal to x plus 1 square? Well, what is the easiest way to draw this thing? So of course, y equal to x squared, just parabola. Y equal to x plus 1 square, this is parabola. But you shift to the left 1 unit. So that means this is your graph. All right, your axis is here, so you get parabola. Oops, parabola y equal to x plus 1 square. All right, so the vertex is negative 1, 0, right? Because you shift to the left 1 unit. And then you want the region that bounded by this parabola, the x-axis, the line x equal to 0 and x equal to 2. So x equal to 0 is here. The axis x equal to 2 is here. This is x equal to 0. This is x equal to 2. And also you need the y-axis, which is here. Well, that means your region is going to be the one that I highlight in light blue. Awesome, right? So now you rotate this thing about the x-axis, which means this is your axis of revolution. Well, if you want to draw a picture, but you don't have to, this is going to be the picture of the solid. Does it make sense? So you're going to get a solid that you, every time you just, I shouldn't do that. This is going to be your solid. Solid is here. So it means you just have the piece that I highlight in light blue, and then you just rotating about the x-axis, so you get a solid. The question asks you to find the volume of this solid, which is called the solid of revolution or the solid by rotation. Sounds good? Well, but to just keep our picture clean, we are not going to just draw the solid. We just use our imagination. It's going to be a solid there. Well, so what are we going to do is we are going to, well, we know that the axis of rotation is x-axis, right? So we're going to compute the volume by using this method. So it's going to be V equal to integrate something to something pi times radius square. So this question, we need the x. Why do we need the x? Because this is how we cut. So we cut perpendicular to the x-axis, right? And we're going to use this thing as our radius. Does it make sense? When you do that, so when you do the rotation, so you're going to use this thing as your radius. Well, you cut every time you get a circle. So that means our radius going to be x plus 1 square minus 0, right? Which is just x plus 1 square. So that means when you do the final version, so you can get integrate pi x plus 1 square, everything square, right? Because radius is x plus 1 square, dx, and then you integrate from 0 to 2. Well, how do I know it from 0 to 2? 0 to 2 is here, 0 to 2, because you have to draw the vertical line from 0 to 2. Good. This will give you, well, let's integrate that. It's not that hard, I think. Integrate 0 to 2 pi x plus 1 to the 4th power dx, which is going to be pi times integrate x plus 1 to the fourth power dx plus 1, x from 0 to 2. Well, that's mean you get pi x plus 1 to the fifth power over 5, x from 0 to 2. 242 pi over 5. All right. Sounds good. Any question? Good, right? You can see this is pretty similar to the previous section, but the cross section are circles. That's it. That's it for this method. So let's do one more example and then we can stop. So the last one for today, example 185. So example 185, so we have the curve xy equal to 2, the y-axis, the line y equal to 1, and y equal to 4, all right? Well, this question is the good one because I'm going to show you how to integrate with respect to y. All right, so we are going to draw the graph, the axis first, x, y. So draw the curve xy equal to 2. What is xy equal to 2? Hyperbola, right? Xy equal to 2, hyperbola. Actually, you have hyperbola here too, but well, at the end, we are going to just look at the positive side. So y-axis here, and then y equal to 1, y equal to 4. All right, so let's do that. Oops, xy equal to 2. And then I change the color here, the blue one, y equal to 1. And the green one, y equal to 4. All right, so that's mean my region of integration, the base. I mean the region before I rotate. This is going to be the one that I highlight in orange. And then you can see that to do the, okay, well, this is the region R. So part A, find the volume of the solid obtained by revolving R about the y-axis. So if your y-axis here, this is going to be your axis of rotation. So what is going to be your volume of the solid? Okay, one thing that you have to keep in mind is, so this is the trick. So I forget to mention this. This is the trick. Not the trick, it's just the key point for you to memorize. If you want to use this method, so this is similar to draw a line perpendicular to the axis of rotation. So if you want to use this method, so you need to draw a line perpendicular to the axis of rotation. What does it mean by saying this thing? So it's mean when you want to compute the volume of the solid here, I have to, the axis of rotation is the y-axis, so I need to draw the line here. It means the horizontal line, because if I draw the horizontal line here, once I rotate, I'm gonna get the circle here, right? I'm gonna get this the cross-sectional area to be circle. This is what I want. I cannot draw the horizontal line because if I I cannot draw the vertical line because if I do the cut parallel to the y-axis and when I rotate, I am well, it's just confusing because you will not get the radius easily, right? Because the radius is going to be something in terms of y. So that means when you use this method, so you have to keep in mind that you're going to use dy for this question. That means you draw the horizontal line uh, on the picture. All right, so I'm going to show you the solution here. So we're going to have v equal to integrate, well, pi times radius square. So we're going to pick dy, right? Because we draw the horizontal line here. So y going to be, let's do it. V going to be, y going to be from 1 to 4, right? Because this is 4 here, this is 1 here. So y going to be from 1 to 4. And I need to figure out the radius. So what is going to be my radius? So what is going to be my radius here? So from the shape I have here, so if I draw the line, horizontal line here, so the function on the right, this is x equal to 2 over y. Right? The function on the left, this is x equal to 0. So my radius is going to be 2 over y minus 0. Sounds good? Because every time I draw the horizontal line, the left hand side is going to be x equal to 0. The right hand side is going to be 2 over y. So that means I get the radius 2 over y minus 0. So now it's easy. So I can just keep going and compute the volume. So it's integrate 1 to 4 pi 4 over y squared dy, which is going to be 4 pi times integrate 1 over y dy, y from 1 to 4. All right, you can do it at home. So this is going to be 3 pi answer. 3 pi unit cube, whatever unit is. Does it make sense? So one more, then part B, and then this is the last one. So part B, if I want to find the volume of the solid obtained by rotating R about the line y equal to 1. What is, I use the line y equal to 1 as my axis of rotation. So what should I do? So here I have x, y. So I'm going to draw the picture first. Well, this is the line y equal to 1. This is the line y equal to 4. And this is going to be my curve, x, y equal to 2. So this time I use y equal to 1 as my axis of rotation. Axis of rotation. So what should I do? So this is my R. And then you can see the axis of rotation is y equal to 1. So now I need to cut perpendicular to the axis of rotation. So I need to cut the vertical line, right? Because if I use the axis of rotation here, so at the end I'm gonna get the solid, well, like that. Well, it's solid, something like that. The solid, you know, the solid. But I cannot draw it here because it's just in 3-dimensional. However, your cross section is going to be like that picture. So every time you do the cross section, so you're gonna get the circle, right? So that means your picture will need to have the vertical line here. And then how do we adjust the integral here? So you can see you're gonna do v equal to integrate from something to something, pi times radius square. Well, now we use the x because without the vertical line. Well, the hardest part is, dang, we need to split into 2 pieces, right? On the first one that we look at, the one that I highlight in light blue, this is you integrate from y equal to 1 to y equal to 4. However, on the second piece that the yellow one, you integrate from y equal to 1 to y equal to 2 over x. Well, again, this is your picture. The first piece that you do the light blue one, here this is going to be the one that you integrate from y equal to 1 to y equal to 4. And the yellow one is you integrate from y equal to 1 to y equal to 2 over x. Right? This is y equal to 1. This is y equal to 1. This is y equal to 4. This is y equal to 2 over x. That means when you do the vertical line here, you need to split your integrals. So that means when you do the volume of the solid of revolution, so you need to integrate from something to something pi. The first piece, which is going to be the one that I highlight in light blue, radius is going to be 4 minus 1 square dx. The second one going to be pi 2 over x minus 1 square dx. Because the radius on the yellow piece going to be 2 minus x, 2 over x minus 1. The radius on the light blue one is going to be 4 minus 1. All right, to figure out the interval of integration, so what is going to be this number? Well, x equal to 0 here, right? Here, this is your cut. What is your x? You need to find it. And then at the end, you have x equal to 2, right? Well, this point, this is the cut where y equal to 2 and y equal to 1. So this is x equal to 2. Right? And this point, the one that you cut between the line that separate the yellow piece and the light blue piece, this is the piece, this is going to be when y equal to 4 and xy equal to 2, so x equal to 1/2. So the cut off here going to be 1/2. All right, and then you integrate it. That is going to be your answer. So you just need to integrate this thing. So the answer going to be 12 pi plus 4 pi log 1 over 4. Well, the rest of the work is just the easy one, but tedious. Well, again, on the exam, we can ask you to stop here because the question gonna say set up the integral, but do not evaluate. So you just set up and then done. But if you wanna compute, up to you. But no more points because full credit since you set up. Sounds good? All right. If you have any question, let me know. Well, we have about 15 minutes left for questions. So if you don't have any question, you can leave now. Thank you for attending for today. But if you have any questions, stay with me and you can ask. Thank you, everyone.